In nuclear power, most neutrons resulting from reactions are fast neutrons or high kinetic energy. A fast neutron is hard for a nucleus to absorb. A slow, or what they would call a thermal neutron, is a much greater probability of being absorbed than a fast neutron. A thermal neutron is one that is in thermal equilibrium with its surroundings. Thus, fast neutrons need to be slowed. They need to be slowed down to become thermal neutrons to enhance their chances of capture so that a nuclear reaction can be sustained. The material in a nuclear reactor that is used to slow down or thermalize the fast neutrons is called the moderator. Materials that meet these specifications include light water containing protium, heavy water which contains deuterium or graphite and beryllium. The moderator material also plays a role in the fuel requirements of a nuclear reactor. The neutron economy is also a factor in reactor control. So for a steady state reactor operation, an increase in neutron production results in an increase in the fission rate and in the power output. If neutron production were to continue to increase, the reactor core would eventually melt down. To change the power level of a reactor, neutron production must be altered, increased or decreased, until the required new power level is reached. The neutron production in a reactor can be altered by means of control rods or chemical shims. Control rods are made of materials that absorb neutrons and thus reduce the number of neutrons that can be absorbed by fissile nuclei. As mined and processed, uranium itself, natural uranium, is composed of 99.2% uranium-238 and 0.7 uranium-235. If the moderator is graphite or heavy water, then natural uranium can be used as a fuel. However, if light water is the moderator, then the amount of uranium-235 in the fuel must be increased from 0.7% to a range of 3.5 to 5%. Enriching uranium to make this happen is expensive and an energy-consuming process. Nuclear reactor configurations are based on the following considerations: the fuel, moderator, the coolant, the control rods, the cost, and containment. This chart from your book kind of categorizes nuclear reactor types and their characteristics. So there's pressurized water, boiling water reactors, pressurized heavy water reactors that are gas-cooled reactors, as well as light water graphite and fast neutron. The most abundant is pressurized water, which numbers in about 264, and each one they can produce about a total of 251 gigawatts, including all of the pressurized water reactors that exist. They have a fuel of enriched uranium and use water as a coolant and water as a moderator. Again, there's about 264 for commercial power of these pressurized water reactors, with about 200 in service as naval propulsion systems. The concept behind this is that the reactor vessel is pressurized to a sufficient pressure so that the coolant, the moderator, is maintained in liquid state. So typically, pressured water reactors operate at about 300 to 325 degrees Celsius and are pressurized up to 16 megapascals. Here's a schematic of a pressurized water reactor. The reactor core is located in the lower portion of the vessel, and the control rods and the drive mechanisms are also depicted here. In addition to the high operating pressure of the reactor vessel, a primary feature is the pair of fluid loops. So you have the high pressure coolant. That loop circulates fluid within the reactor core and to a steam generator. In the steam generator, the hot, high-pressure fluid is used to make steam at a much lower pressure compared with the reactor coolant loop that is circulated outside the containment structure to the turbine and generator. Here's a view of the reactor core with all the elements, control rods, travel housing, and so forth. And here's the reactor vessel itself. Another type of reactor would be a boiling water reactor. And this one is the second most popular reactor type. A boiling water reactor differs from a pressure water reactor in a few different, in several important features. One, the pressure in a reactor vessel is much lower since steam is the desired fluid. And a boiling water reactor essentially contains only a single fluid loop. Then steam is generated in the reactor vessel and directed outside the containment structure to the turbine. So again, here you can see a schematic of a BWR. You have the core, you have the steam line directly to the turbine generator, and then here you have the condensate coming back out, going through a series of processes, and the feed water brought back to the reactor vessel. Here is a view of the reactor assembly for a BWR, very similar to that of the PWR. Then you have what they would call pressurized heavy water reactors. So as the name implies, heavy water is used in this as the moderator. The reactor temperature in this case is about 290 Celsius. Pressurized heavy water reactors offer certain advantages over pressurized water and boiling water reactors. In this case, heavy water is used as the moderator, so the uranium fuel does not have to be enriched. They can be refueled without shutting down the reactor, and they are not as expensive to build and operate as some of the other reactor types. Here's a schematic of a pressurized heavy water reactor. You have here the heavy water moderator, the reactor itself, the steam generator, which takes heavy coolant water, produces steam here to go ahead to the turbine to produce electricity. Then we also have, which is the last one we're going to look at, gas-cooled reactors. A gas-cooled reactor uses carbon dioxide as a coolant and graphite as a moderator. So these gas coolant reactors allow the use of natural uranium as a fuel. Carbon dioxide is an effective coolant and does not absorb neutrons, with the reactor being about 650 C. In this case, graphite is used as the moderator. Here's a simple schematic of a gas-cooled reactor. Again, you have the reactor here, the graphite moderator, and you have, again, the steam generator here that would produce steam that goes to a turbine. Here's the status of at least a selected number of new nuclear reactor designs from companies such as Westinghouse and General Electric, Mitsubishi, Unistar, and so forth. So with Westinghouse having a reactor called the AP1000, which is rated to put out 1 gigawatt of power.